Hello everyone, welcome to the channel Physics Fun. So in this video, we are going to discuss what is the shape of a catenary. Catenary, it is basically a heavy rope. And this question is inspired from one of the questions of two questions of the book David Morin. So this is very, very important for JEE Advanced. The JEE Advanced directly, it is not in the syllabus, but it can definitely come as a comprehension. And for Olympiad students, it is very, very important. So what we are going to figure out that this shape, the shape you're seeing here, this shape is, if this is a heavy rope, then this shape is actually a cos hyperbolic function, right? So immediately, without wasting any time, let us get on with the analysis. So here now, we are going to find the equation of catenary. And this is the diagram. This is point A, this is point B, and this red color is the heavy rope. I am taking the origin here, this point where slope is 0. So this is my x-axis and this is my y-axis. So in this analysis, we are from physics point of view, we are going to use two very, very important results, which I think I will explain also. So one is that x component of tension force in the string remains constant, right? That is obvious because if you draw the free body diagram here, then suppose if I draw the free body diagram of this part of the rope. So when I draw free body diagram, here suppose tension is T1, here tension is T2. And if you take this component here, suppose it is theta1, here it is theta2, then we can write that T1 cos theta1 is equal to T2 cos theta2 because there is no other force in x direction. But what about y coordinate? Y coordinate is different. The y component of tension is different because it has to balance weight of this part, right? So that thing also we will be using. Now, another important thing is that tension in the string is along the tangent. It's very obvious point, but it is going to be very useful in this analysis. In fact, we are going to start with this point only. Tension at any point in the string, if you cut the string from here, then tension is along the tangent, right? And now, before finding the final result, I want you to know this. Maybe if you probably know hyperbolic functions, then it's fine. Otherwise, hyperbolic functions are nothing. Just that cos hyperbolic function is e power x plus e power minus x divided by 2. Sine hyperbolic function is 1 upon 2 e power x minus e power minus x. So that is sine hyperbolic function. And then inverse of sine hyperbolic function is this, right? So you can check this. If you take sine of sine inverse, you are going to get 1. And cos hyperbolic function, there is a minus also here, but if you see the domain is different, right? So this is the maths part. I'm not going into too much detail of this. Let us now get on with the analysis. So here, this is the first point, right? I said I will start from here. So at any point in the string, let us say this point. See here, this point. This is Tx and this is Ty, right? And Ty by Tx is equal to the slope because net tension force is pointing in the direction of tangent. See here, net tension force is pointing in the direction of tangent, right? So if it is pointing in the direction of tangent, then you get this diagram. This is Tx and this is Ty and this is the net tension force, right? This angle is suppose theta. So slope at this point is tan theta, which is dy by dx. So Ty by Tx is dy by dx. That is one very important point. And then here Ty now I'm writing as Tx times dy by dx. What is Tx now? Here comes the first point. X component of tension remains constant. So if X component of tension remains constant, then that I'm writing as C, right? Which is a constant value. So we can keep this as Tx only, but it's better since it is constant. So we can write this as C. Fine, moving on. So this is then Ty is equal to C dy by dx. So I have marked this as one equation. Now, another very important point, which we were discussing here from this diagram, you can see the y component of tension differs because of this weight component, right? So the difference of y component is, suppose here, this is y component of tension. This is acting downward. The difference between these two is the weight, right? So the difference is actually d of Ty, fine, which is equal to the weight. That is why the tension in upward direction is increasing because it has to support the weight of this part. So that is what I have written here, d of Ty. That means the difference in the y component of tension is nothing but dmg. Dm is lambda. This is a uniform rope and dl is this length, right? Dl is this length. This is a very small, just for understanding purpose, I have drawn it like this. So dty is equal to lambda tlg. Now, little bit of simplification, which you might be knowing. Now, dl here, since this is a very small part, so I have drawn this as almost a straight line. This is dl, this is dy, this is dx, right? So dl here is root over dx square plus dy square. Dl here is the length, right? Length of the curve. So length of the curve is nothing but, see here, root over dx square plus dy square. This thing you use in when you derive the formula of radius of curvature of any curve. 1 plus dy by dx whole square, that formula. So dl here is, I can take dx common, right? So here you get 1, here you get dy by dx. Fine. Now, later on in next line, I'm going to use dy by dx as y prime, because next order uh, differential equation is going to come. Second order differential equation is going to come, right? Okay, so now follow very carefully. Keep writing also. This is one equation. Ty is this. This is another equation, right? And here now see dty, this equation. Now the second equation I am writing in a different form using this as dl, right? So dty is equal to lambda and g you can see as it is. dl I have substituted as dx 1 plus y prime whole square. So dy by dx I have written as y prime. Fine. Now see d of ty by dx, right? From here, now I'm moving to the next step. So d of ty by dx is equal to lambda g 1 plus y prime whole square. Is that understood? Now see, from 1, this is equation 1. If you differentiate this once more, you get dy by dx, right? Which is equal to what? C d square y by dx. So that I can write here. So if I differentiate this, you get dy by dx. Equation 1, I'm differentiating. C is constant, remember? D square y by dx square, right? So that is what I have done here. Dy by dx, I am now substituting from here, right? So this becomes then C d square y by dx square is lambda g 1 plus y prime whole square. So now d square y by dx square, I have written y double prime. So y double prime is equal to lambda g 1 plus y prime whole square. Right now you have the idea what to do next. So I am now putting y prime as z, dy by dx as z, assuming another variable. So here this becomes a very simple differential equation. Z prime is equal to lambda g by c. What was c? Remember, c was the x component of tension. Lambda is mass per unit length, g is g, gravity. So 1 plus z square, right? So then now we can rearrange dz divided by this, separate the variables, and here. Right? Now you know the integration of this. You might be knowing in a different way, but the integration of this is nothing but the inverse of hyperbolic function. So I'm integrating from where to where? See, I'm integrating from 0 to z, right? So that is also a very important thing for you to see. Z is actually the slope, right? So I have taken the origin here, I have taken the origin here. So here slope is 0, right? So that is why my integration starts from 0, goes up to z. And this starts from x coordinate is 0, it goes up to x. So integration of this is sine hyperbolic function inverse z, and then these are the limits alpha x. Now sine hyperbolic inverse 0, let us see. So sine inverse hyperbolic is this. So put x equal to 0, you're going to get 0, right? So that is how, see here, sine hyperbolic inverse, this one is when you put 0, it becomes 0. So only this function is left. So you get z as this, right? After that, it's simple. Z is basically the slope of the actual curve, right? So we are now going to the next level, next step. So z is dy by dx. We put dy by dx here. This is sine hyperbolic function. And now differentiate 0 to x and 0 to y. And then now when you differentiate this, y is equal to cos h alpha x divided by alpha, right? So if you have not studied hyperbolic function in maths, then simply that hyperbolic function is, see, what is hyperbolic function? These are the hyperbolic functions, right? So instead of writing hyperbolic function, you can just write e power x. If you know the formula of integration and differentiation in terms of e power x and e power minus x, no problem. You can keep writing that also. So here now what do we get? 0 to y sine hyperbolic x and dx. Integrate the 0 to x. Cos hyperbolic 0 is how much, right? Because this is the lower limit. Let us see. Cos hyperbolic 0 is how much? This is the formula of cos hyperbolic 0, right? X equal to 0 if you put, this is 1, right? 1 plus 1 by 2. So that's 1. So that is how you got this as 1, right? But this one is not important. This depends on the choice of origin. So if you choose origin such that, this one might become 0 also. So this is the main function, cos hyperbolic alpha x divided by alpha, right? Now, it is very, very important for us to see that what is alpha, and alpha depends on what. So alpha depends on lambda, g, and c. What is c? C here is the x component of tangent, right? So this is the final answer which you got. This is the cos hyperbolic function. Now, there are many questions in Pathfinder which are based on heavy rope, but in none of the questions, actually, uh, you have to solve for the equation of trajectory, right? But if you know the equation of trajectory, then it might help you in many Olympiad questions or many other questions also. If you know that trajectory is cos hyperbolic functions, fine. Okay, so now based on this, after learning this, you can try two questions of David Morin. So that questions now, those questions I'll show you now. So these are two questions. This is 2.8, right? Page number 50. And this is from the chapter of statics. There is a chapter of statics in David Morin. And this has two parts, right? Very, very good questions. And this is another question. In this also you will have to, in this function is already given. You will have to calculate alpha, right? So if you have understood, try these questions, and the solutions are also given. You can go through the solutions, and once you go through the solutions, and if you understand the solution, you're going to learn a lot about heavy topic. Fine, so I'm going back here now. So this was my analysis. If you have liked this analysis, then please subscribe to this channel and please like this video also. And then I have made one more video on heavy rope, that also the link of that video also I will put in the description. In that video, I have, without calculating this, I have explained how to calculate the tension force. So link you will find in the description box. You can watch that video also. Based on that video, you can solve all the questions of Pathfinder, which includes heavy rope. Fine. So thank you very much for watching, and please like this video. See you next time. Thank you.